dependence. And in this example, let me open my data. So so we're here. I know it's in downloads, so let's go there. Uh, Let it load. And pretty much you can see it just below here. I'm going to open this file, JASP file, and there. So while waiting, this is actually a file. Here we go. This is a fictitious data set called Titanic Survival, and this is a classic data set that shows 1,313. You can see it here. That's our sample or population size. We have 1,313 passengers, and we are just interested to know their nominal sex variable and whether they survived or not. Okay, so in this example, again, we have sex, male or female, and survive, either yes or no. So in this video, I would use JASP in order for us to answer the question, is there a significant correlation between survival and sex? So let's go ahead and click on what we're going to do is going to click the frequencies option here. I'm going to click this and you'll be given a number of options, but we're only going to use contingency table. So I'm going to click right that, right? So this will give me this kind of setup, and always remember, sorry, this is the input part, this is the output. So you just, in the input, you tell JASP what to do, JASP will do it for you then. So we're gonna input our independent variable by convention, though it's clear that there's no independent dependent variable in chi-square test or any test of associations. But by convention, we input the independent variable on the columns, and the dependent variable is placed on the rows. So we're gonna put the survived in the row and sex on the columns. And right after that, we're gonna click some things. Okay, so what we want to do, I'm gonna click this one here. I want to check the chi-square, continuity correction, the likelihood ratio as well. And in the nominal, since both of them are nominal, I'm gonna click on the contingency coefficient and the phi and Kramer's phi. In the cells part, what I'm gonna do is I want to check on the expected frequencies for me to check their expected frequencies and not always only the observed ones. I want to show the percentage of row and column, and I want to check on the Pearson's residuals. This is a form of a post hoc testing, which tells us if the observed counts and expected counts are significantly different. Okay, so we only refer to this when there is a significant association that happens. We may disregard this value if there's none. Okay, now what we need to do then is we need to look at the contingency table. So we're actually, the table in a simple manner shows us the observed frequencies and the expected frequencies. This is the chi-square table, where it shows the value of the chi-square and the p-values as well, and the this one here, the phi coefficient and Kramer's v, tells us the strength of the correlation. So first, we want to check the assumptions of the test. So remember, in a chi-square, the most important assumption is there should be less than 20% of the cells that have an expected count of less than 5. Okay, and none of the cells should have an expected count of less than 1. So from this table, we just need to highlight the expected counts. You can see it here, 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 and here. Of course, here as well. So you can see that all expected counts are surely more than 100. The lowest is 177. So we have no problem in that assumption. So you can always compute if you want to make sure that it's less than 20%. So in this case, it's gonna be 0% surely. Okay, so the next part that we might want to look at is the percentage within rows. You can see this form here and this row here. So from this table, we can see that the percentage within rows, um, it tells us that more males died on the Titanic. So we can see that 84% died, which are males, and only 15% died, which are females. Okay, so you can remember maybe in the movie, shall we say, that most of those who were given the spaces on the boats and the lifeboats were females and children. So maybe that's the case, but we don't want that the kind of question. We want to know if there's an association about the survival and the sex. So, is there a significant association? Even though we can say that more males died and more females survived, and which can be also verified in the yes in the survival, but is there a significant correlation? So the chi-square test will indeed tell us that. So let us go to the next table right here. So this is the chi-square value, chi-square continuity correction, and likelihood ratio. Um, by default, we are to use the chi-square, the first row in this table. So how do we report it properly? Let me see if I can take some notes here. Yeah, I can add some notes. How do we report this is like this. Can I put the chi? Oh, no, I cannot. I'm just gonna put x if you don't mind. Hopefully you don't mind. Um, okay, there you go. Chi-square. And the next part I'm gonna put is a df. So df is 1 equals 365.89. Gonna round it up. And comma p-value is less than 0.001. So that's how we properly report the statistics. So what does it tell us? Remember the decision rule that if the p-value is less than your alpha, there is a significant relationship between survival and sex. Okay, so we only focus on the first row. What are the purposes of these things here? We usually use the chi-square continuity correction. Actually, this is used to prevent overestimation of the statistical significance for small data sets. This is used when at least one of the cell of the table has expected frequency smaller than 5. Okay, though in enough values, they will be similar. Their values will be similar to the regular Pearson's chi-square. Okay, so just a word of caution. This continuity correction here may overcorrect and result in an overly conservative result that fails to reject the null hypothesis when it should be. So that will tell us or give us a type 1 error. So or type 2 error. So just be careful with that. Regarding the likelihood ratio, it is an alternative to the Pearson chi-square and it is based on the maximum likelihood theory. For large samples, it is identical to the Pearson's chi-square. But when do we use this? This is recommended for in particularly small sample sizes like less than 30. So since our sample size is enough, more than 1,000, 1,300, 1,313 to be exact, we will have no problem with sample size. And um, the major problem with chi-square tests is that it doesn't inform us the strength of the relationship. It only informs us, well, that there is a significant relationship, but it doesn't tell us how strong, or it doesn't give us the magnitude of any association. So we have here two options: the phi coefficient and the Kramer's V. Now, what's the difference? The Kramer's V is the most popular to be used. In most cases, we use the Kramer's V if the number of rows and columns are more than 2 by 2. But if the contingency table is 2 by 2. Similarly here, it's 2 by 2 because we have two categories for the sex, two categories for the survival. It's going to be phi coefficient. The phi coefficient is more appropriate for 2 by 2 tables. Otherwise, we will use Kramer's V. Okay, I hope you understand that. And how do we determine the strength then? We can actually see the value from Champion way back 1981. But there's a new table by Kim. This was 2017. They are also called as the effect sizes of the chi-square test. For Kramer's V, it will be small if it's 0.1, moderate 4.3, large 4.5, and it differs on the degrees of freedom that we have. Okay, so I'll send you the link for the table, but um, you can see we're gonna make use of Kramer's V in this case surely because we have a 2 by 2. It's 0.53, and 0.53 is way beyond the scale. It has a large effect or a strong correlation, a large association.